Almost everyone knows of the adjustable spanner, so when Johansson patented the idea back in the 1890s, you would think that the Allen key equivalent wouldn't be too far behind. Actually, the Allen bolt itself wasn't invented until the 1900s, but I think we've given the world enough time to come up with a solution. So in this video, let's have a go at designing and making the world's first adjustable Allen key. My first thought was segmenting the Allen key into 6 sections and then pulling a wedge up through the middle, which would then force each segment to spring open. To explore this idea further, I slit a piece of hex bar on the milling machine to simulate a simplified version of the concept. Each segment has to be quite long to allow it to spring open, and this highlighted the first significant challenge straight away. When an Allen key is used to tighten a bolt, it's subject to significant torsional stress, which is really shear stress. Let me explain in the case of pure bending first. This is a bar of solid material. In bending, it has a certain stiffness. Now let's chop it up into multiple thinner sections. The bar is made of the same material and has the same overall dimensions, but it can now bend much more easily because each segment can slide relative to its neighbours. We have exactly the same problem with our adjustable Allen key. Each segment can slide relative to each other, significantly reducing its torsional stiffness and consequently its effectiveness. Now I think I have an idea how to solve this problem, so let's get started with its construction and I will explain along the way. It begins with a piece of silver steel bar 13mm in diameter. Once turned down, I drill a small hole up through the middle to help with slitting shortly. It's then mounted in the milling machine where I mill the hex shape which will form the basis of the Allen key. In this concept, I thought the torsional stiffness could be improved by reducing the length and increasing the width of the flexible portion of the segments. And instead of making the flexible portion part of the same component as the Allen key itself, I decided to make them separately as flat springs. This meant I could only section the hexagon into 3 segments to make space for the wider springs, but I don't see why this should be a problem. This project is part of the 2025 Toolroom Takeover collaboration, where several machinists and metalworkers from YouTube make something for each other. This project is for Nick from Jonesy Makes, so let's hope we can get something that works for his sake. At the end of the video, we will also reveal what James from Cloud42 made for us. To fix the flat springs to the Allen key, I milled on 3 flats the same width as the springs will be. An important thing to note here is that the flats are not milled on the same plane as the flats on the hexagon. This is because it's best for the adjustable Allen key to engage in the corners of the Allen bolt and not the flats. The segment is drilled to take the fixing bolts, and the component is then chopped into 3 equal parts. Earlier, I proposed pulling a wedge up the middle to spring open the Allen key to a larger size, but the problem with this design is that the Allen key prongs, for want of a better word, would have to be hollowed out significantly to make space for the wedge and suitable pull rod, which would weaken the prongs. It would also limit the range the Allen key could expand. So to solve this, I machined a cone behind the prongs, which are held in the collet with shims in the gaps, by the way. I can then use a push rod instead. I decided to make the contacting portion of the push rod hemispherical. There's no point in making it a cone because the angle of the internal cone will change depending on the size the Allen key is set to. The springs are machined from annealed tool steel, and some time can be saved by using the holes to align the parts and finishing them off together. These need to be heat treated so they don't plastically deform in use, so I made a stainless steel pot with a handle to safely hold the parts, whilst keeping them protected from the atmosphere in boric acid. After quenching, the springs warped unfortunately, but I decided that they were good enough to proceed since I didn't even know if this design was going to work yet. The Allen key prongs were also heat treated. Before I even got a chance to properly test the concept, I broke one of the prongs, so I had to remake them, except on the second attempt I forgot that crucial step I mentioned earlier, which was to make sure the springs were aligned with the corners of the hexagon, not the flats. These ones also turned out a bit wonky, but again at this stage I thought good enough. Initial testing looks promising. This is a bolt going into a tight nylock nut. If I remove one of the segments, hopefully this will give you a better idea of how the concept works. You can see the brass hemisphere has seen quite a bit of wear already, which is not ideal, but you can also see how the brass hemisphere engages with the cone. I was happy with the Allen key at finger torque levels, but when I tried to measure it with the torque wrench, I couldn't even get to 2 Newton meters before it slipped in the bolt head. The reason is because although the mechanism was stiff enough in torsion, the prongs could flex inwards. This issue was exacerbated by trying to engage on the flats of the bolt rather than the corners. I decided that this was just a bad design, and clearly I should have done some maths on the bending stiffness of the springs rather than just guessing it. So I decided to go back to the drawing board. After some head scratching and a total of 6 different concepts modelled, I came up with what I thought was the sure thing. I reduced the number of prongs down to 2 so they could be made thicker and stronger than before. The prongs are supported in a slotted block, providing improved torsional stiffness, and the push rod is now a chisel shape to increase the contact area with the prongs. In this design, the prongs are now hinged to improve the overall rigidity. As before, the prongs need to be heat treated, so I made them from tool steel, this time starting with square bar. I used the watchmaker's lathe to machine the hexagon shape. The geometry is more complex than with the previous design because I have to machine a compound angle. To achieve the correct angles, I needed to compensate for the compound angle and the fact that the centre of rotation is not actually at the centre of the hexagon with the prong mounted in the machine this way. I also changed my heat treatment approach and used charcoal powder to prevent oxidization rather than the boric acid I used earlier. The boric acid can form a hard glass-like substance after quenching, which can trap small parts like this if I'm not careful. The prongs are tempered to a blue to provide the optimum material properties for this application. The hinged block is made from a tough steel. I machined a groove in the outside so I can fit some kind of spring to keep the prongs in contact with the central wedge. I don't know what the spring is going to look like yet, but I thought we could cross that bridge when we get to it. And again, before I even got a chance to film it, I broke yet another prong. I was worried that I got the heat treatment wrong, but here you can see some plastic deformation on the intact prong, so I think the temper was about right, but it was the geometry that was wrong. I spent some time experimenting with lots of different prong geometries, and this is what I came up with. The prong is carefully designed to provide strength at the root, and the angles in both planes were optimized such that the engagement with the bolt provides strength and stability. I also refined the wedge by playing around with different shapes and tempers. Here, the prongs aren't actually quite in their final stage yet, but they're good enough to go through some thorough testing. And after lots of use around the workshop, in a range of applications, I was really happy with its performance, and you can see only a negligible amount of wear after some pretty extensive use. And importantly, I couldn't get the prongs to break. Of course, I can't pass it on to Nick in this prototype state, so I made a nice handle to contain the adjustment mechanism and finish the overall package. This part of the device really is quite open. I thought it would be nice as a screwdriver-like tool, so that's what I set out to make, but I see no reason why it couldn't be miniaturized if the traditional L shape is preferred. As far as I can tell, this invention is novel. It will work on any Allen bolt from 4 to 6mm, imperial or metric. This range is quite narrow, but I feel confident that the range could be extended with a little bit of extra design refinement. The closest thing to this that I'm aware of is the Telehex Kickstarter project, which is essentially a nested Allen key, but please do let me know in the comments if you've ever encountered an adjustable Allen key before. We did consider patenting the concept, but instead we decided to publish the drawings and CAD on our Patreon, so anybody can have a go at making one. This includes the screwdriver handle that I'm making here, so head over to Patreon if you're interested in that. For the adjustment knob that will fit into the handle, I used a metric fine thread to provide more sensitivity to the adjustment mechanism. At this point in the project, I was pretty keen to race through the rest of it, and decided to save a few precious minutes by using a die to cut the adjuster thread. Of course, in the end I had to recut the thread properly anyway, so it was made to a good enough standard. I also decided to machine flutes on the knob instead of knurling it. Personally, I usually prefer fluting unless it needs to be really grippy. I machined a hemispherical cap to cover the adjusting knob using this ball turning attachment to prevent the adjuster from being accidentally altered when using the Allen key. I always find these cheap carbide inserts leave a rubbish finish, so need some tweaking to get the best performance. The cap is held in position with an O-ring, so it can simply be pulled off if the Allen key needs adjusting, and pushed on when the setting is correct. I discovered that the mechanism needed a return spring when adjusting the Allen key from a large size to a small size, so I fitted a cross pin in the push rod, and a normal pen spring provided adequate force. For the spring to keep the prongs pressed against the wedge, I tried various options such as O-rings, circlips and wire snap rings. In the end I had to make a custom spring, but if this was going to be mass manufactured I would adjust the design so an off-the-shelf part would work. With all the parts made, I glued it together with retaining compounds and lubricated it with oil on the push rod and grease where the wedge makes contact with the prongs. In practice I found it worked fine without lubrication, but I like to do a proper job with the assembly. This is a 4mm bolt, and I've tightened the vice jaw so I can crank the bolt nice and tight. Now let's adjust it for 6mm. And again I can tighten the bolt with as much force as I can put through the handle with no issue. This is what the prongs look like close up. My Myford tool post Allen bolts are 3/16, which is 4.8mm. The adjustable Allen key works perfectly here, allowing me to tighten up the bolts securely. I definitely don't have to worry about my tool coming loose. No problems with my bicycle axle, which is 6mm. So I guess the question remains, is this a viable invention or just a neat party trick? To be honest, I don't know. It does genuinely work very well, but although I tried my best to minimise the head diameter, it's still quite bulky and will often not reach in certain situations. But the main problem is that normal Allen keys are just so cheap and easy to manufacture. As I mentioned earlier in the video, this project is one of several for the Toolroom Takeover YouTube collaboration. The adjustable Allen key was made for Nick from Jonesy Makes, so be sure to check out his excellent channel. But before you do, we need to have a look at what James from Cloud42 made for us. If you've ever tried to measure a gap against a flat surface, you'll be aware what a pain it can be. James's tool solves this problem. It's a graduated wedge, where the graduations align with the thickness of the wedge. He's done an incredible job on this. It's lovingly made from A2 tool steel and heat treated to 57 Rockwell, which is about as hard as a good quality knife. The surface has been ground to a gorgeous finish, and he's even engraved Cronova's logo on it. Extra points for it being on the metric side. Thanks for the tool, James. We're really looking forward to putting it to good use. If you want to see how he made it, check out his Toolroom Takeover video at Cloud42, and likewise if you want to see what Nick thought to our Allen key, check out his video over at Jonesy Makes. And thanks to Eric with a K for organising the collaboration. If you want to help support our channel and access extra content, including detailed plans on how to make the adjustable Allen key, please check out our Patreon page. See you in the next video.